Hello everyone, welcome to this live stream. My name is Janaki Ram, Jani, based out of Hyderabad. Today I want to walk you through an end-to-end demo that I have built around event-driven RAG pipelines on Kubernetes. I have shown this a couple of weeks ago at KubeCon Europe in Paris, got tremendous response, and I thought I will do a quick replay of the demo and also take this opportunity to give you details around how I went about building this. So let me first share my screen and then show you what I have in place. So first I'm going to show you uh, a chatbot which is representing a fictitious airlines company. So the idea of this is it is helping customers get some queries answered about their itinerary, their trip, and in general about the airlines. So this demo has three parts. The first part is what I'm going to show you, which is the actual live demo, which is the chatbot. Once I finish this, I'll walk you through the architecture, and then we'll get down to the infrastructure and the code and look at how I went about building that. And in that process, I'll also tell you some of the tips and some of the tricks that I have found when I was building this entire Gen AI stack on Kubernetes. So coming back to the first part of the demo, so here is the fictitious airlines offering a chatbot to its customers. Let's call this as Redjet AI, Redjet AI Assistant, your travel co-pilot. So basically, this can help answer some questions like what is the excess baggage fee? Now, initially, this chatbot has no context. There is absolutely no information provided to the chatbot. So it comes back with the standard response, which is, I don't know, can you please provide more context and information about airline or air travel? Now, what I'm going to do is I'll switch to my command line and I will basically add a PDF that looks like this. So this is the terms and conditions and the baggage policies of the airlines. So this is the entire PDF, and there is a specific paragraph about baggage fee and excess baggage allowance. So it says the excess baggage fee is 25 euros per kg for domestic flights and 20 euros per kg for international flights. Oversized baggage fee is 45 euros. So this is the PDF. Now what I'm going to do is I will copy this to my data lake. So the data lake is where I'm going to store all my unstructured data, whether it is PDFs or txt files or word docs or whatever. So let me copy v1 uh, into my data lake. So this gets copied. Now I come back to the chatbot and ask exactly the same question, what is the excess baggage fee? And now you actually notice that earlier it said I don't know. Now, because of the context we provided, it is able to say the baggage fee is 25 euro for domestic and 30 euro for international. Yeah, 20 for internationals. Yeah, so it basically picked up from this. Now, one of the challenges with RAG is as soon as we update the data, it is going to be eventually available to the chatbot. So what I'm going to do is now I'm going to show you another version of this baggage policy document. And let's say the airlines on a specific date has updated the baggage policies, bumping up the excess baggage fee from 25 to 30 euros for domestic and from 20 to 25 for international. And even the oversized baggage fee has gone up to 50 euros from 45. So now what I'm going to do is I will come back to my command line and update my data lake with the v2 of the PDF. So now this gets copied, and let's come back to the chatbot and ask exactly the same question again. So now, as soon as we are done, you can actually see that the chatbot has picked up the most recent context. And now it actually shows us 30, which is what we have updated in the document. Now, let's say there has been a mistake. Someone in the airlines ops team has committed a problem, a mistake, and they have gone with this too soon. So now they need to revert. So now we'll actually overwrite, come back to the chatbot, and ask the chatbot, and it instantly reverts back. So that is the actual demo which I wanted to show you. And what is serverless, what is event driven about this, is what I'm going to demystify as we go along. So this is the basic chatbot. You can actually ask some questions, it comes back and responds. Uh, Now, what is unique about this is not running OpenAI, this is not running Anthropic Claude or anything. This is all running on a single node Kubernetes cluster within my lab. So here is the big picture and the architecture which I have been sharing on LinkedIn. So this is the PDF. We upload the PDF to the data lake, which is MinIO. And MinIO has, just like Amazon S3 supports Lambda as an event trigger, it supports a variety of event triggers, and I have chosen webhook. So as soon as we upload a PDF to MinIO, the webhook gets triggered, and the job of this webhook is basically split this uh, into multiple chunks, call the embeddings model, which is the Beijing Academy of AI, the large BAE, large embeddings model, convert every chunk into a vector embeddings, and then call Chroma and ingest all the embeddings into the Chroma vector database, and that finishes the phase one. So in phase two, we actually have the chatbot UI built using Gradio, and Gradio talks to Mistral 7 billion parameter LLM running again on Kubernetes. And when we basically ask a question, the context gets pulled through the semantic search from the vector database, and it gets fed to Mistral. And because Mistral has the context, it comes back and without any hallucination, it gives us factually correct response. So this is the big picture. And this entire stack that you're seeing is basically running on a single node Kubernetes cluster. So this is part two of what I want to show you. Part one was the actual demo, which is the Gradio interface. And this is part two, which is the big picture, the architecture. So um, I hope you are able to follow. Um, if you are able to if you're able to see the screen, just type comments and I will get to see it here. Okay, so assuming you are able to follow this, so that basically completes the second part. Now what we'll do is switch to the third part, third section of this demo, which is the meatier part, and where I want to really spend some more time giving you the details into how I went about building this stack. So let me close this. I don't need it anymore. We'll come back to this. Before I go ahead, what I'm going to do is I will undeploy my entire application. I don't need it anymore. We'll come back and deploy every component of this step by step. So all right, okay, so thanks for sharing the feedback. Great that you're able to follow this stream. All right, so I have shown you the chatbot, I have shown you the big picture, the architecture, and now it is time for us to look at the infrastructure. There are multiple layers of this infrastructure. So let me first show you my GenAI testbed. So this GenAI testbed is running in my lab, and this runs a fairly powerful CPU. This runs an Intel i9 14 Gen with multiple cores. There are about 32 cores. It's a pretty powerful CPU, and I have about 128 GB of RAM. So that's the core compute and the memory. Now, when it comes to the GPUs, I have two RTX 4090s. Currently, they are not utilized. You can actually see that they are not consuming any VRAM. I have a couple of them. It's a purpose-built, uh, highly customized PC that runs two GPUs with a whopping 2000 watt power supply unit. Housing these two massive GeForce RTX 4090s has been a challenge. So I have gone ahead and ripped off the chassis and the cabinet to make them fit into this. But that's the hardware, the CPU, the memory, and the GPU. So that forms the core compute. Of course, I have uh, two SSDs coming to about 2 TB each. So I have one 2 TB disk dedicated to pull the models exclusively from Hugging Face. The other 2 TB is partitioned, and I basically use that for my projects and my data. So that's the storage, 4 TB of storage. All right, so that's the core compute infrastructure. And if you are wondering what I'm running, well, this is running on Ubuntu 22.04. So that's the operating system. And I have the latest NVIDIA drivers installed. We have already seen that. Let me show you one more time. So I have the 545 2308 and CUDA version 12.3. So that is my next layer, which is the CUDA layer. So NVIDIA drivers and CUDA. So this is all set up. Now I have Docker. So the next step is installing Docker, because I run containers directly on my Gen A testbed without using Kubernetes. So it's very handy to run Docker, even though it is not directly connected to Kubernetes. I use this to test BentoML and a variety of containers directly on the OS. And I, of course, have uh, container D running. Now, once I installed both Docker Community Edition, Docker Engine, and Container D, I install the NVIDIA Container Toolkit. What it basically does is, if you actually look at the docker daemon.json, it basically changes the default container runtime to NVIDIA Container Runtime. Now, this is a very crucial step. What this basically does is it surfaces the CUDA and the NVIDIA drivers to containers. So you can now actually run Docker containers and give them access to the underlying GPU. So this is the most important step. So both Container D and Docker are configured with the NVIDIA Container Toolkit so that they have access to the underlying GPUs. Once this is all done, I have gone ahead and installed upstream Kubernetes. So if you actually look at my Kubernetes infrastructure, it was installed 86 days ago, right after the New Year holidays, and I haven't touched that since then. So this is my single node Kubernetes cluster, and this actually runs a few things. So if you look at the namespaces, I am running NVIDIA device plugin. So NVIDIA device plugin is basically the link between kubelet and the NVIDIA Container Toolkit, because you need to expose the GPUs not just to containers but all the way up to the Kubernetes layer. So I chose NVIDIA device plugin. The other option is NVIDIA GPU operator, but if I install that, I lose access to GPUs at the OS level, because NVIDIA GPU operator takes over the CUDA installation, the NVIDIA drivers, and makes it very hard for me to access the GPUs from the OS. Now, I use this in three different forms. One is I have Jupyter notebooks that are directly running on my machine. Uh, so, that gives me access directly with pip install Jupyter, and I can access GPUs and Hugging Face models. Second is I can run containers. Third is I can basically use Kubernetes, but all of them share the same underlying infrastructure. And because CUDA is so critical for all of these environments, particularly three environments, I installed NVIDIA drivers and CUDA separately, and then connected that with the NVIDIA device plugin. Now, if I install GPU operator, I don't have to install CUDA and NVIDIA drivers separately, but it also takes away the flexibility of running this directly on the OS, because you can only access the CUDA runtime, a CUDA layer, only through Kubernetes. That is the side effect of installing the GPU operator. Now, that is the device plugin. If you actually do kubectl describe nodes, it basically comes back with some pretty interesting metadata. So I also installed what is called as the NVIDIA discovery. It is basically the feature discovery, NFD. So what it does is it introspects the node and then automatically adds a bunch of labels. So if you actually look at these feature.node.kubernetes. These are all added by the NVIDIA feature discovery capability. And it is actually a flag that you provide when you are installing NVIDIA device plugin. It is basically a Helm chart setting. So once that is done, you will see a bunch of NFD and nvidia.com/CUDA. So all these labels get added, which are pretty, actually, these are the feature.node.kubernetes are the default metadata, but the nvidia.com labels are basically added by NFT. So now if you actually look at how my node is described, it shows the CUDA driver. And if you remember, this matches my NVIDIA SMI command. It shows the GPU count. I have 2. It shows the GPU family, Ampere, and it also shows the product name and the GPU replicas, MIG capable. MIG is basically the multi-instance GPU. It is not supported on Ampere and particularly consumer grade RTX 4090, so that is false. Now, the advantage of having this is you can now use this to set the GPU limits and requests when you're deploying GPU specific pods. So this is extremely critical for you to bring the node affinity and node anti-affinity into the picture. So that's my Kubernetes cluster, and the NVIDIA device plugin is already installed. I have also gone ahead and installed the Metal LB system. That's my bare metal load balancer. I have Nginx Ingress, nothing fancy, but the most important aspect of this cluster is it is running the NVIDIA device plugin. All right, so now we have a pretty powerful single node Kubernetes cluster with 2 GPUs, and our goal is to run an entire Gen AI stack and a RAG pipeline just within the cluster. The core assumption is even if you disconnect that from the internet, it should still run. None of the data points will ever cross the perimeter of your data center or your network, and it should be pretty capable and perform really well. So those are some of the assumptions and prerequisites I had in mind when I built this. So now let me switch to my other command line. So now I'll walk you through the YAML files that I assembled to put this stack together. So the first one, let me start with the most obvious. So I create a namespace called the stack, and then I create a config map, and this config map is super critical. I actually define the service names for the internal discovery, and because everything is running within the same namespace, I don't need to prefix this with anything else, so the discovery happens pretty naturally. So this is min.io, min.io access key, secret key, and this is the webhook that I am using to basically split chunk the PDF and generate embeddings and talk to Chroma. This is the port number. This is the alias of min.io. This is the bucket name. This is the alias for ChromaDB, my service name, port, and then I'm actually running an embeddings model using an inference server from Hugging Face called TEI, Text Embeddings Inference. More on that later. And then I am running LLM inference based on TGI, Hugging Face Text Generation Inference, pretty powerful inference server. The collection name within Chroma is called PDFs. So that is the config map. So let me go ahead and run those two first. So first we'll deploy the namespace, and then we'll deploy the config map. Okay, so those two are pretty straightforward. And then comes in the LLM. So now there are some specific tweaks that I have done to this stack, to make sure I get what I want. So basically my requirement is to share the Hugging Face model repository across 3 different environments. One is Jupyter Notebook running directly on my machine. Second is Docker containers that I'm going to run. Third is through Kubernetes. Now, I don't want each of these environments to pull Hugging Face models every time I access through these environments. So I want to basically share the repository, the model repo, across all these 3 environments. I don't want to end up pulling them every time. So for that, what I've done is on my local machine, I basically created a directory called HF, and I pointed the Hugging Face CLI to this directory. So here, if you actually see, I have the models like Mistral 7B Instruct, Metalama 7B Chat, and so on. So this is my centralized repo. Now, if you actually look at my, I think I have this here. Let me see if I can. I somewhere actually said this. I'm not sure where I configured, but basically I made sure the Hugging Face client is pointing to this, and every time I use Hugging Face anywhere, whether it is through Jupyter Notebook or through Kubernetes or through Docker containers, they all point to exactly the same location. Now what I do is I point the same host path to my pod. So here I create a new persistent volume pointing that to the HF hub, and then I put some node selectors. This is not the best practice. I'm going to move this to NFS and use NFS provisioner, but I'll talk about that towards the end on the enhancements I want to do to this stack. But this is basically a local host path. I'm actually using a storage class which is local path from Rancher. So from this PV, I create a PVC. I call this local storage, and this is my HF API token. I create the deployment. Now, when I'm creating the deployment, I use Hugging Face text generation inference. So this container image is pretty powerful. So let me show you what it actually means. So I will launch another browser window and take you to HF TGI. So Hugging Face text generation inference, if you're not familiar with it, is my favorite text generation LLM inference server. It's fantastic, supports a variety of models which are currently topping the leaderboard, and it gives you everything to basically host models locally. Now, why do you want to use this? Because Hugging Face themselves actually run on this. Now, if you go to, for example, uh, if you go to Mistral AI and look at the Mistral 7B instruct model and look at deploy, so you see this inference API serverless and inference endpoints dedicated. Now, guess what? The inference endpoint dedicated is actually running TGI. So Hugging Face in production runs text-gen inference, and currently there are tens of thousands of spaces that are currently leveraging that container image. So why not use that? And not only that, just 2 days ago, Cloudflare has partnered with Hugging Face to bring serverless container to their edge. And guess what? They're also using TGI on their POP infrastructure, point of presence edge locations. So TGI is pretty powerful, and I rely on this to expose my LLMs as an endpoint. Basically, it's an inference server. And if you look at the parameters, I basically pass the Mistral AI 7B instruct, the previous revision 0.1, and then this is where the power comes in. Because of the GPU NFD, the NVIDIA feature discovery capability, I can now say, just like I ask for CPUs, I can say, give me one GPU to run this pod. And then I use the HF token, which is my API token, to pull the model, and I basically mount the local host path, uh, and then I expose this through the load balancer, and I hardwired my IP address because I have a lot of clients that talk to this endpoint. I didn't want this to be very ad hoc and very random. So I have hardwired the load balancer IP. So pretty straightforward. A PV pointing to the model catalog running locally, and then the TGI container which is running Mistral and then exposed as a service. So now let's go ahead and deploy that. So this is my llm.yaml. So if you look at what's running within my namespace called stack, you actually see there is one container called LLM. So let's look at the logs. It should be pretty fast. It's already in running mode because I've cached everything and I'm pointing this to okay, so this is running and listening on the port. The IP address says 0000, which means it is readily available. And then if you look at the service, it's already exposed as an endpoint 10.10.10.3. So that is my LLM, the core building block. Once we have the LLM, then comes in the embeddings model. So we need the embeddings model because we want to perform semantic search. So for embeddings model, I use pretty much the same technique. I create a dedicated PV. I give 200 gig, but it need not be that. But I'm mounting the same directory on my host because I have that already running here. So if you look at OPT data HF hub, you actually see that I'm running the BGE large EN v1.5. That is the model that I'm launching within this. So everything remains the same. Here, I run the text embeddings inference. So text embeddings inference is again an open source container from Hugging Face. You can again, excuse me, you can get this on GitHub. You have like a pretty well documented page here, and similarly, you can even read about it on the Hugging Face documentation. This is a very handy container. It does more than serving the embeddings model. It supports re-ranking models, which I'm actually planning to use within my stack. So this is my most preferred inference server for exposing embeddings endpoint. All right. So what am I running here? Well, it is the BGE large EN v1.5. When I built this stack a couple of months ago, this was the top leading embedding model on the massive text embeddings leaderboard. Now, of course, there are Cohere, Command R, and are like much better models. But even today, when it comes to open source, this is one of the best embeddings model. And now I give another GPU to this. Now, interestingly, when we look at what is going on with my NVIDIA GPUs, you actually see that 20, almost 24 GB is consumed by Mistral. But my second GPU is underutilized. So that is what I want to do. Now, when I actually say GPU 1, request GPU 1, the scheduling engine figures that I have two GPUs, one is already busy, so it automatically schedules this on my second GPU. So again, I expose this as a load balancer endpoint. I give a static IP address. So let's go ahead and run this. So I have my next thing coming up, embeddings.yaml. And now when we get the service endpoints, we have the embeddings available at 4. And when we look at the deploy, we have two deployments. One is the LLM, the other one is embeddings. So the pod should be ready instantly. Within 6-7 seconds, it becomes available because everything is cached. All right. So now we are done with the core LLM and the embeddings. What next? Well, the next one is the vector DB, right? So that is pretty straightforward. So what I do here is I take the official Chroma image and I run this here, nothing special. I make this persistent because I want to save the data. So this is listening on load balancer static IP. So let's go ahead and deploy this. So that is going to be vector db. Oops. Okay, so now a PVC deployment and a service for Chroma are in place. So now when we get the pods, we have the vector DB running. So that is the most important building block. This is where we store the embeddings. So after that comes in storage.yaml. So what is storage? Well, storage.yaml is actually my data lake. So what I do here is again, use my host path uh, where I persist the data, and then I launch the official MinIO server. I pass the access key and secret key that I created in the namespace, the config map, and then I simply expose this on a static IP address. Nothing special. But MinIO is a very important aspect because all the PDFs that power the RAG pipeline essentially live in this storage layer. So let's deploy MinIO. So now when we look at what we have here, we have LLM embeddings, vector DB, and storage. All of them are running, all of them are up to date. Perfect. So now we need to do some plumbing, and that plumbing is basically connecting the webhook with MinIO, because as soon as we upload a PDF to MinIO, we want the webhook to trigger the chunking process, generating the embeddings, and then push them into the vector database. So that's where I have the webhook. So if you look at webhook, this is my custom image. Uh, I don't have time to show you the source code, but it basically does three things. As soon as the webhook post is invoked from MinIO, it first chunks the PDF sentence by sentence. I'm not sure if that is the best strategy, but for this demo, I chose the sentence based chunking, and it creates a list, sends all the chunks from this list to the text embeddings inference endpoint, gets back the vectors, pushes them, which is the second part, and third part is pushing them into Chroma, and it basically waits for the next request. And similarly, the webhook also has a delete endpoint, and as soon as I delete a document, uh, it again goes ahead, refreshes the collection by either overwriting or deleting the entire collection. So this is the webhook part. Now this webhook needs to be deployed after we create the job. So let me look at the sequence. Yes. So first we need to deploy the webhook. So let's go ahead and deploy the webhook. All right. So now when we look at the number of deployments, we have almost everything coming together. This is the data lake. This is the webhook. This is embeddings. This is the vector database. Perfect. Okay. So now comes in the plumbing part, and that is the storage job. So what we need to do is we have multiple moving parts. We have the embeddings model, we have the vector database, we have the MinIO, but how do we bring all of them together and connect the dots? How do we tell MinIO that every time something is uploaded to this bucket called PDFs, do this? That's exactly what I do in this job. So here I run a set of MinIO commands. I say this is basically using the MinIO MC client image, and I run this as a run to completion job in Kubernetes. It basically connects to MinIO, and then it removes the alias if it is already there, and then it adds the webhook. If you actually see event MC event add, it adds the event for both put, which is adding the PDF, and I also give the prefix as .pdf, and I also create an event for delete, because we want to delete the entire collection as soon as the PDF is removed. So I create this webhook, and then I basically exit the job. So pretty straightforward. This is where we do the plumbing, connecting all the dots together and making sure we are able to uh, bring the serverless and the event driven capabilities into the picture. So now the last part almost is running the storage job, and this is the most fragile part. So I want to basically watch how this all turns out. So, oh, this is completed. Perfect. So now if I actually look at the logs of the job, what it basically does is, it added the MinIO webhook. It created S3 object created webhook. Pretty cool. I really love MinIO for this. And it also created a webhook for the event called S3 object removed. It is very close to how S3 and Lambda interact with each other. So this is all done. So now we have the entire infrastructure in place. And then finally, it's time for us to deploy the chatbot. So here comes the chatbot. And chatbot is again a very simple Gradio interface, nothing fancy. I don't even use LangChain because I wanted to keep this very transparent. LangChain will bring in a lot of abstraction. So for the demo, I wanted to keep this very transparent and completely relatable and understandable. So I'm not using LangChain. So if you look at, I can show you the code. Uh, Yeah, so this is my Gradio code. It basically gets the LLM URL, embeddings URL, vector DB, and then it creates a system prompt. You are a helpful AI assistant based on the context, blah blah blah, and then it generates the context by taking the query. Query is chroma, gets the context, and then it creates the chat completion by embedding the final prompt, which consists of both the system prompt and the user prompt. And the user prompt basically has the context and the query, and we run the chatbot interface with some preceded questions like what is the excess baggage fee and so on. So what I did is I've gone ahead and dockerized this. So this is a Docker file, nothing specific. It basically takes the Python image and then pushes my app.py into it, nothing fancy. So this is my chatbot, and chatbot is also a web app. So obviously I give a static IP to it, and then I deploy this. And this is the final step, the moment of truth. So let me show you how it all pans out. So now we have the entire stack up and running. So okay, so we have everything. Going back to my architecture, this is what uh, we have deployed: MinIO, webhook, embeddings model, LLM, vector database, and the chatbot. Pretty straightforward, but the beauty is it's all running on cloud native infrastructure. All right, so now let me come back and refresh my chatbot. Blank slate, we don't have anything here. I'll ask, what is the excess baggage fee? It says, I don't know. Now we'll repeat these steps. We will copy V1, ask exactly the same question, and now it comes back and confirms it is 25 euros per kg. Now we will overwrite with V2, ask the same question, it gets updated. Now I will go ahead and remove and ask the same question, it reverts to I don't know what you say. So this is pretty cool. This is what is event driven retrieval augmented generation pipeline based on cloud native infrastructure and running the entire stack just within a concealed, confined environment. I can go ahead, pull the plug of my router, and it still works without leaking any of my data to any endpoints outside of my network. So this is what I wanted to share with you. Now, a couple of caveats and also the roadmap for this demo. A lot of people ask me, when am I going to share the code and the entire deployment artifacts? I'm going to do that very soon. I'm cleaning this up a little bit. I built a pretty scrappy version of this just for the sake of demo, and it works. It is pretty solid. I did multiple tests and it works well, but I need to clean up this a little bit, number one. Number two, there are a few things that I want to bring into this architecture. Number one is webhook is not the best scalable mechanism. I want to move to NATs and use cloud events and basically replace that with a more asynchronous, more scalable technique to asynchronously convert my PDFs into embeddings. So I'm going to replace the webhook with a message-oriented middleware, something like NATs. That is number one. Number two, I want to implement CADA, because currently what happens is, if you look at my NVIDIA SMI utilization through an NVIDIA SMI, so the embeddings model is taking very less memory, but the LLM is taking almost 100%. And if there are no requests, it still keeps running. Not an ideal thing. And the other thing is, if I want to run a Docker container directly while this is still running, I obviously cannot do, because one of my pods is consuming and annihilating the entire GPU. So what I want to do is, I want to implement CADA and bring scale to 0. So with CADA, I can actually configure a metric that says, if HFTGI, which is Hugging Face Text Gen Inference Server's HTTP request queue is idle or 0 for a specific time window, scale it to 0. Now, the advantage of that is it saves power, it makes it more sustainable, and also it gives me back the GPU when I'm not running any chatbots through Kubernetes. So I want to bring CADA. And I also want to experiment with knative serving, because knative serving also supports scale to 0. And I want to bring the Prometheus and Grafana capability, so that I can actually create a custom metrics for all of this. Because currently it's very hard to understand how many tokens are being sent, how many tokens are received, what is the token per second that I am able to generate. None of those metrics are currently available. So I want to actually figure out how I can get it out of the box, or if required, write a custom exporter to basically get some of the LLM specific insights through Prometheus and surface that through Grafana, and then use the standard NVIDIA GPU metrics to basically look at my GPU utilization through Grafana dashboard. So I want to bring observability into this, and I also want to apply guardrails. So all of these are in my roadmap, and I'm going to add them one at a time. But very soon I'm going to clean this up and put it out there on GitHub and do a detailed session on how you can actually go about installing. I have kind of compiled and almost ready with all the scripts, all the way from installing the NVIDIA driver to the Gradio code. I have everything. I just need to clean it up and do a commit to my repo and turn that repo to public. So I'm going to do that very soon. So that's the demo which I wanted to show you. So I hope you found this useful. Um, if you have questions and if you're watching this from LinkedIn, just leave some comments. I will try to respond to you as soon as I can. And don't ask me about code. It is going to be available very soon. So thanks again. Thanks for signing up for this and watching the live stream. I will bring additional demos very soon. Thank you.